Futurama.
I need clothes.
They ruined all.
But now I'm in school, so I watch
They ruined all.
nothing.
Quick reminder about tomorrow.
They didn't explain much either.
No lecture.
No sock.
No lecture Thursday so that we can enjoy.
What?
Like, yep, we just
Yeah.
more
Whatever you want to enjoy. Take advantage of it. I really was so confused my first summer living out here teaching that they were like, you can't teach on July 24th. I was like doing the math in my head. It's 20 days after the 4th of July. It's like a month and a half before Labor Day. I don't know. What is it? What's the joke? All right. Yesterday we started looking at reactions that give us alkynes. Today we're going to start looking at reactions with alkynes. Most of these are going to be addition reactions. But I'm actually going to introduce a substitution reaction to us first. We're going to review the substitution then in a little bit as well. This reaction, though, is considered alkylation. So, halogenation, you get halogen groups in your compound. Hydrogenation, you get hydrogen. Hydration, you get water. Epoxidation, you get an epoxide. What does alkylation give you? Not an alkyne. An alkyl group. What is an alkyl group? Not a carbon to hydrogen. Or sorry. Just carbon group. Did you say carbon to oxygen?
No.
Oh, okay. Just a carbon group. Like we talk about alkyl halide. Just a carbon group. We talk about our alkyl substituents, methyl, ethyl, isopropyl, tert-butyl. This is what we consider alkyl. So one of our alkyne reactions is to take an alkyne and put on it, not hydrogens, not halogens, but a carbon chain. This is a substitution reaction. So I just want to make that clear. We're not looking at an addition reaction yet. We're actually looking at our first substitution reaction. There's actually two parts required for alkylating. First, we need to deprotonate a terminal alkyne. This creates a nucleophile, a carbon that's willing to share its electrons. So if I were to give us something generic, this would be a terminal alkyne. And we need to react this terminal alkyne with something that is a better base than the conjugate base of the alkyne. So coming back to our table on our homepage, scrolling past the functional groups, here's an alkyne. Alkyne has a pKa around 25. So that means I want to use a base whose conjugate acid has a pKa greater than 25. I want whatever acid that forms to be bad at being an acid so that my equilibrium does not reverse. So that means I could use amines or the conjugate base of amines, amides, not to be confused with the carbonyl group, the amide. I could use hydride. I could also use sp2 hybridized carbons or sp3 hybridized carbons. The most common thing that you'll see used here, though, is sodium amide or sodium hydride. We get a couple of byproducts, which is, of course, a sodium ion that balances this carbanion, and we get ammonia or hydrogen as the conjugate acid. And this carbanion will not deprotonate ammonia or hydrogen because they are weaker acids than the alkynes anyways. So our equilibrium is favored in the forward direction. What we have just done is created a nucleophilic carbon. The second step in doing alkylation we'll substitute an alkyl halide. Preference for primary alkyl halides. Low substitution. Methyl or primary. Not very often secondary. So in a generic form, we take this alkyne anion and we react it with some alkyl halide. And I'm going to say here R prime, only because I've got R here, and these R groups don't have to be the same. I'm just saying that it's bonded to something. And the product we get is an internal alkyne. I have taken a terminal alkyne, I have alkylated it, given it an alkyl group. Now it's not terminal anymore. So let's look at some examples together. Let's take one butine, deprotonate it with sodium amide, alkylate it with bromomethane. Now I like to map my carbons to make sure that I know where everything is going to be. And I actually like to count through a nucleophilic attack. By the way, I guess I wanted to point out, if this is our nucleophile right here, that makes this an electrophile. It's going to accept electrons. So my nucleophilic carbon is here at the end of my alkyne. My electrophilic carbon is just a methyl carbon. The product I get is 2-pentyne. What do you think? Taken an alkyne and I've alkylated it. Okay, well, we actually know that we can start adding several steps together. So I don't need to start with an alkyne either. Let's look at an example where I form a terminal alkyne and alkylate it right away. One dichloro, 3-methyl butane. How many equivalences required to take this geminal dihalide into an alkyne? 2 equivalences of strong base. Does that set me up for alkylation? No. I need to deprotonate that terminal base as well. With what? the same, sorry, I said that wrong. Need to deprotonate that terminal alkyne with that same base. So I'm going to add 2 equivalences to form the alkyne and a third equivalence to deprotonate that terminal alkyne. 3 equivalences. So I'm saying 2 equivalences form the alkyne. That third equivalence deprotonates it, makes it a nucleophile. Maddie, give me a number between 4 and 8, please.
4.
Bummer. Okay.
I almost said 6.
6 would have been nicer, yeah. Chloromethyl cyclobutane. That's a cyclobutane that's substituted by a methyl group, but the methyl group is also substituted by a chloro group. So this is chloromethyl cyclobutane. Now, here's how I'm going to number my carbons. From the right-hand side, I'm going to number to carbon 4. That's going to be the terminal carbon of the alkyne. That's going to be the carbon that acts as this nucleophile. Carbon 4 is going to attack carbon 5, substituting the chlorine and then connecting it to this ring. So here's my final product, alkyne. Carbons 1, 2, 3, 4. I formed that alkyne in the first step with my base. I also deprotonated the alkyne. 4 attacks 5. And 5 is bonded to cyclobutane. And that looks really funky. Carbon 5, carbon 6. Notice how carbon 5 lost its bond to chlorine, gained a bond to the alkyne. Carbon 5 went through substitution. The alkyne became alkylated. I now have 1 cyclobutyl, 4 methyl, 2 pentyne. I know it's not numbered that way by nomenclature, but this is just mapping. This is just helping me keep track of all of my atoms. Okay, I do want to show you guys a little bit of what this mechanism looks like in case that helps you understand it more. Here's the alkyne anion intermediate that forms. And here's my electrophile. It's just a very simple alkyne carbon donates electrons, chlorine takes electrons. The bonds substitute each other. That's it. Nucleophile attacks electrophile. A group leaves the electrophile. The chlorine is a leaving group.
So what would the byproduct of this?
Good question. First of all, this is going to create some ammonia byproducts. And then this is going to be kicked off as a chloride. Plus, it'll be balanced by an Na from that first step. So you would expect a byproduct of chloride, Cl-, or more realistically, sodium chloride.
When you say 3 equivalents, is that like stoichiometrically or 3 different steps?
Well, both. It is stoichiometric. If I have just one equivalence of Na and H2, I do one elimination, I get an alkene, a vinyl halide alkene. The second equivalence removes the second halide, gives me the alkyne. The third equivalence deprotonates that alkyne and gives me the alkyne anion.
So if you were like doing this reaction though, you just put like three, like
Get one-
stoichiometrically three to one.
Get 1 mole of this reagent, you need to add 3 moles of this reagent. Or, better yet, an excess amount of this reagent, like more than 3 moles. I want to look at another one with you guys, which is what happens when we start with acetylene, C2H2. Acetylene is not just a terminal alkyne, correct? It's like a di-terminal alkyne.
Why is it called acetylene?
Why isn't it called acetylene? It's a really good question. I don't think there's a good answer. The ACET prefix often refers to a 2-carbon group that contains a carbonyl, a CO double bond. That's it. So it seems like they took this compound and assumed, what if you did another elimination and made it an alkene, but it's actually an alkyne? I don't know. I don't get it. It should be acetylene, but it's acetylene. This is a di-terminal alkyne, which means I can alkylate it twice. Now, of course, it would be very easy to alkylate both sides of the alkyne with the same group. Just have 2 equivalences of NaNH2 and 2 equivalences of your electrophile, and both sides of the alkyne become symmetrically substituted, symmetrically alkylated. But it can be more useful to do this in 2 separate steps and to get 2 different alkyl groups and create an asymmetric alkyne. So I'm going to look at these as carbon 1 and carbon 2. I'm adding in this methyl group, so that'll be carbon 3. And then I'm adding in this benzyl group, so that'll be carbon 4, and the benzene ring would be carbon 5, or group 5. Here's my triple bond. Let's say that carbon 2 bonds to carbon 3, and let's say that carbon 1 bonds to carbon 4, which has the aromatic ring attached as well. I have dialkylated my alkyne. I can only do that with acetylene. Acetylene. Dang it. I can only do that with acetylene because it's the only one that can be deprotonated twice. And we could stop here and we could show all of the intermediates. First, I make an acetylide ion. Then I make an alkylated alkyne. Then I make a second acetylide ion. And then I make this dialkylated alkyne, this internal alkyne. You guys comfortable with this? No? Taking a carbon chain and we are building on it. Taking 2 carbons, ending up with 6, 10 total carbons.
What is it again that's turning one side into a negative charge, into a?
The base.
Okay.
Simple acid-base reaction.
We're just pulling off the proton.
This is NH2 minus. It bonds to the proton. CH bond goes back to the alkyne.
I guess I gotta train myself to remember that we have hydrogens on these just like we do any other.
100%. I often refer to those as pesky hydrogens because they're hidden. So if I can encourage you to do anything, it would be to draw in hydrogens anytime you need to. Draw in the hydrogens here. Remind yourself that carbon 2 has 2 hydrogens, just like it did here when it said CH2. You just need to be careful that you don't come to an alkyne like this and draw in hydrogens that aren't there. You've got to check your octet rules all the time. All right, that's alkylation. You could say this is another way to prepare alkynes, but technically you have to have an alkyne already in order to alkylate it. If anything, it's a way to prepare internal alkynes from terminal alkynes. All right, no questions on this? And everybody's caught up with the board? No one needs a picture or anything? Now that we've got more of us in here, I just want to reiterate, tomorrow we are not meeting for class. I'll try to send an announcement about it today as well, but Pioneer Day tomorrow. State holiday, so the school is closed. Okay. On to our addition reactions. The rest of these will be very similar to our alkene reactions. We'll start with halogenation. How many equivalences of halogen could an alkene take on? Okay, to be fair, when I say a halogen, I mean elemental halogen, like X2. 1 equivalence for an alkene. 2 actual halogen atoms. How many equivalences of a halogen, elemental halogen, can an alkyne take on? It's got 2 pi bonds, so it can do twice as many addition reactions. So I like to give you guys these generic versions, but I'm going to have to actually break them down into a couple of different forms. What if we have just 1 equivalence of X2? Okay, I think black's dying, so we're going to have to use a different color for this. Regiochemistry. Let's describe the regiochemistry of this product that forms. Vicinal, vinyl, dihalide. Correct? The halogens are on 2 separate carbons, adjacent to each other, and they're connected to an alkene. That makes them vinyl. What about the stereochemistry about this reaction? Anti. This is anti-addition. That means I'm going to get a trans-alkene. You guys see how the halogens are trans to each other? Those halogens, they're going to be the high priority groups. So we've got anti-addition here. Guess how much more challenging its mechanism is compared to the mechanism of alkene halogenation? It's no more challenging in any way. First, a halonium ring forms. This is a bit of an odd halonium ring. Because it's got this double bond between the carbons still. And this halonium ring is flat. The alkyne starts linear, but the halonium ring forms on a plane. And the halide ion, it just substitutes anti. It has to attack from exactly opposite where the halonium ring is. That's what gives us our anti-addition mechanism. That's exactly the same as what we saw in alkene halogenation. All right, we need to see what happens though if we have an excess amount of X2, if we have two equivalences or more. We should predict that first, this vicinal vinyl dihalide forms, which is just an alkene, and then the alkene reacts in the way that we would expect with the second equivalence, and it does halogenation. In terms of regiochemistry, we can call this a vicinal tetrahalide. How many chiral carbons form in a reaction like this? None. So in terms of stereochemistry, there's nothing to talk about. Yes, the mechanism proceeds via anti-addition, but you get these two carbons with two identical groups, so there's nothing to see. And in terms of the mechanism, it follows exactly the same as this. So I'm just going to start off with ... And then it reacts exactly the way that we saw alkenes react. Halonium ring forms. Yes, this halonium ring is a little bit different because it's already got halogens connected to the carbons. And then the halonium ring gets opened. Are you guys okay with the fact that I just used generic X2 and not a specific halogen? You understand you could swap that with bromine, with chlorine, with iodine. Less so with fluorine, but that's okay. All right. Reaction 3. HX addition. Once again, we're going to need to look at what happens if we have one equivalence of HX. This time, I'm actually going to give us a different generic alkyne. Let's look at a terminal alkyne, because the regiochemistry here is more relevant. One equivalence of HX adds H to the less substituted carbon, X to the more substituted carbon. So in terms of regiochemistry, we would describe this as Markovnikov addition. And it gives us a vinyl halide. Now, this is something that you're not going to see often, but the stereochemistry of this is considered random addition. With our alkenes, random addition meant if two chiral carbons form, all possible combinations of those configurations will form. But with one addition of HX, we don't form chiral carbons. So it means if an alkene stereocenter forms, E or Z alkenes, both combinations will form, E and Z. With what kind of preference do you expect? Well, no. Preference for the trans alkene, the lower energy alkene. All right, how different do you suspect this mechanism is compared to our alkene HX addition mechanism? Very good. It's not different at all. I'm just pandering to you guys. HX is an acid or a base? HX is an acid, so what is the base? The alkyne is the base. Pi bond from the alkyne attacks HX, breaks the HX bond. Which carbon of this less substituted alkyne is more partial negative? Which carbon of this terminal alkyne is less substituted and more negative? Really got away from me there. This is more negative, this is more positive. Remember we said more substituted carbons always have more positive character. Less substituted carbons always more negative character. So who uses the pi electrons? Partial negative carbon. Who loses the electrons? Partial positive. In the next step, which carbon takes on a positive charge? The more substituted carbon. CH becomes CH2. Internal carbon stays internal, takes on a positive charge. What is the hybridization of this carbocation? This carbocation is bonded to an R group and a CH2 group. Two groups. This carbon started sp, and it still is sp. Very similar to alkenes, which start sp2, and then the carbocation that forms is also sp2.
Would you draw an end to that point or no?
Tell me, is an sp carbon organized bent? It looks very odd that I've drawn this as a linear structure, but it's sp hybridized, so it is very much linear. Is that okay? If you drew this bent, I wouldn't mark you off points, but I would think less of you. I'm just kidding. Could you imagine?
Yes.
Yeah. Halide attacks. Gives me the vinyl halide. How different is that from our alkene HX addition? The only difference is that you've got an alkyne to work with instead of an alkene. You've got two pi bonds to work with instead of one. Okay, let's look at what happens when we get two equivalences of HX. My generic reaction, HX in excess or two equivalences. Talk to me about the regiochemistry. Yes, say it again louder.
Geminal.
Geminal what? It is Markovnikov still. Geminal halide? Not quite. Dihalide. Good. So Markovnikov addition, that makes sense. But this gives me a geminal dihalide. Stereochemistry? Relevant? No, because I add 2 H's to 1 carbon, 2 X's to 1 carbon. No chiral carbons ever form in this X2 to equivalence addition. Once again with the mechanism, I'm going to lead up to it with this dot, 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 because the first equivalence is exactly the same. It's the second equivalence that reminds us more of our alkene addition reaction. Pi bond attacks H, gives me a carbocation intermediate. Halide attacks the carbocation and gives me a geminal dihalide. All right, let's do some practice problems. Can you predict the product that forms from 2-pentyne reacting with 2 equivalences of Cl2? And to go from 2-pentyne to 2,2-dibromopentane, can you give me the reagents and the missing product? No, this is not quite right. And this is not quite right. This is actually correct. This is not. No, not quite. I'm glad I did these examples the way I did because I can see the confusion that these 2 types of reactions give. If you want to, right, you could try writing out the IUPAC name of the compound that forms for the reagents. Now, some of you might think you work better showing a mechanism to get to the final products. I think understanding mechanisms are great, But I also want you to be able to use that regiochemistry as a way to predict what the functional group looks like quicker than having to show the mechanism. It might help though if you map your carbons, because that will tell you something needs to go on this carbon, something needs to go on that carbon. Wherever you want to start. That's the beauty of mapping, is you can take it to your advantage however you want. Correct. Good job. Actually, sorry. The subscript doesn't exist. Otherwise, it would be HX. There you go. That's it. BR itself doesn't exist. Could be BR2 or it could be HBr. That's what you have to decide. If it helps though, look at the functional group of the product and figure out whether HX got us there or X2 gets us there. Yeah. Why don't you guys take a couple of extra minutes to turn into the people around you, talk with one another. What are you identifying that helps you predict the product? What are you feeling confused about in predicting the product or the reagents? That's the right one. This is not. Oh, not necessarily, no.
That's so 2 and 3 are the Alkynes, 2 and 3 are the Yes. I got nothing. I'm getting confused between
Maybe I'm kind of off.
Maybe that's what it was. Because you do look like a kind of misunderstanding on it. Do you got?
I realize. Like
Could be the same.
Well, we've got CL2 in excess. Our regiochemistry told us that when we get tetra, so I would start by figuring out how long is your carbon chain. Just redraw that carbon chain as just a straight out. And then figure out which positions are going to turn into the tetra.
Good. That's it. Yep. Sweet. Good job. Instead of bromines, they will be chlorines.
Whoa.
But you've got the right idea there. And this is not quite right, and this will not work. Not quite. No. And this is not it. I'm sorry. That's what I'm here for. Yeah.
I never have to redraw.
We should get the right
You got it.
I got it. That's when they use
This is missing an arrow.
Yep, okay.
And this is missing an arrow.
Yes, it's gonna go to
Carbon is not an electron.
There you go.
I don't like when you have a triangle and then the atom outside of it. It's better that those bonds actually point.
Yeah. I realized that after I drew, I was like, I don't want to erase it. But I gotcha.
Because this is elemental chlorine. It's chlorine bonded to chlorine. Look at, I erased it already, but in the mechanism I even draw it as X bonded to X. X2. But H bond. So it's not HX2. Yeah? Bet. All right, guys. What did you find? I didn't hear a lot of communication, but I see you guys kind of in your groups. What do you think about predicting these reactions? What are you struggling with differentiating?
I was confused that the examples are HX, but these sample problems start with a dihalide. Is it the same or different?
Okay, to be fair, I didn't give examples for the X2 addition. So you have examples here of both X2 addition and HX addition. That was the goal. I wanted you guys to actually solve problems for both types of reactions at the same time so that you can differentiate what reagent am I going to use. But maybe this is why you were struggling to say HX always gives a geminal dihalide, and I saw a lot of people here that gave me a geminal dihalide. But Cl2 is not HX addition, and it does not give a geminal dihalide. This gives a tetrahalide. So 2 equivalences of Cl2, that's 4 total Cl atoms. And they add across carbons 2 and 3. So if you're mapping your carbons, you can say here's an alkyne carbon, that'll become a geminal dihalide. Here's an alkyne carbon, that becomes a geminal dihalide. In this reaction, it's only carbon 2 that becomes a geminal dihalide. So what else was added? What was added to carbon 3? 2 hydrogens were added. So I saw a number of people that were putting Br2 here, but Br2 isn't a source of hydrogen. So where does the hydrogen come from? This is generated by HBr, not Br2. In my example, I only gave you a terminal alkyne. And I told you the terminal alkyne always forms a geminal dihalide. What I didn't give you an example of was an internal alkyne. And so here I highlight for you whether it's terminal or internal. I think you guys will agree with me that internal alkynes don't follow Markovnikov or anti-Markovnikov because an internal alkyne doesn't have a more substituted carbon and a less substituted carbon. Internal alkynes are equally substituted. Markovnikov doesn't apply. Do you agree? Even internal alkynes still give us geminal dihalides. But if it can give me a geminal dihalide on carbon 2, which is equally substituted as carbon 3, then I should also be able to get a geminal dihalide on carbon 3. Those of you that had your unit test this weekend, and you were asked to predict the missing structural isomer in your HX addition reaction, this is the exact same issue. Both carbons are equally substituted. Both carbons could equally likely become the carbocation, so I get 2 structural isomers.
So if it was anti-Markovnikov, you'd have a Br and an H on each carbon, right?
No, if it was anti-Markovnikov, it still wouldn't apply here. It would only apply to something that's terminal. Markovnikov and anti-Markovnikov, in terms of regiochemistry, only means something if one carbon is more substituted than the other. What you're saying, if I got one H and one Br on both carbons, it doesn't happen in any addition reaction that we're going to go through unless you combine different addition reactions.
Sure.
And so you would have to just describe, once you invent it, you can get it named after yourself.
Can you just repeat what Markovnikov means again?
Anybody else want to give it a shot? What does Markovnikov mean? How does it apply?
It's like something that has more H's gets more H's.
Yep. The carbon with more H takes the H.
That's why it's only the end. Okay.
Carbon with the H takes the 2 H's. Carbon with the H takes the 1 H. Does this have a carbon with more H's? No. And remember, Markovnikov's rule is bad because it's not about H's, it's about substitution, stability of the positive charge. So here, is one carbon more substituted than the other? No. So Markovnikov's rule doesn't apply. I still get geminal dihalides. It's just that I get geminal dihalides on carbon 2 and on carbon 3.
Is that one that you just erased?
Yeah.
That was kind of what you were saying, was really with the like negative, slightly negative, slightly positive.
Only if it's terminal does Markovnikov's rule ever apply.
For example 2, would you not say HBr excess?
Ah, yes, you can. Actually, that would be best. HBr 2 equivalences or HBr excess. Thank you. Good catch. Can you guys, anybody tell me, was the confusion here the fact that I had both a halogenation and an HX addition together?
I think I just thought because we were doing the examples from like the
Yeah.
HX edition that we weren't talking about the other one.
But now, so maybe if you need to in your notes, after X2 addition, say examples below HX. Because I didn't give you an example problem with X2 addition, did I? I'm pretty sure I didn't. So I wasn't trying to trick you there, but I wonder if that was maybe what impeded you guys answering those. Okay. Moving through our addition reactions, our next one, 4. Let's do hydration. There's actually 2 hydration reactions, so maybe it would be worth putting this in parentheses and referring to the actual reaction as oxymercuration, a hydration reaction. There is regiochemistry here, so I'm going to use this terminal alkyne to indicate this. You guys remember oxymercuration from alkene addition? But it was followed by another name, reduction. This is not followed by reduction. And it's not quite the same reagents either. This is mercury sulfate and sulfuric acid with water, not mercury acetate in water followed by sodium hydroxide or sodium borohydride. We're going to add an equivalence of H and OH, and it's going to add Markovnikov. But I want you to be careful about this structure right here. This hydration product is called an enol. And enols in acidic conditions preferably tautomerize into carbonyls. So what is isolated is a ketone. So we're going to lay out some of those words again. First, regiochemistry, Markovnikov, gives us a ketone. I go from an sp carbon to an sp2 carbon and a carbon that has 2 H's, so stereochemistry is just not relevant. There's nothing to talk about here. We're not going to go through this mechanism, but I do want to lay down this idea of tautomers a little bit more. Tautomers are structural isomers that can be chemically converted between each other. Not all structural isomers can be chemically converted. Hexane, 2-methylpentane, those cannot be chemically converted between each other. They are structural isomers. Tautomers are structural isomers that can be chemically converted. Notice what's happening in the structural isomerism, in the tautomerization. The OH hydrogen is taken down by the CH2 group to make a CH3. And the pi bond moves between carbon and the oxygen. This equilibrium arrow that I'm showing says prefers the carbonyl rather than preferring the enol. Reaction number 5. Hydroboration oxidation. Once again, a hydration reaction. We're going to keep this same alkyne. We'll react it with borane followed by basic aqueous potassium hydroxide. Potassium, oh my goodness, sorry. Basic aqueous hydrogen peroxide. Putting my P's and H's all over the place. This is anti-addition, which means, once again, I form an enol that is not isolated, but instead is catalyzed in these basic conditions into an aldehyde. So the regiochemistry is anti-Markovnikov, and the functional group that we get here is an aldehyde. Stereochemistry, once again, not relevant.
And when you're saying that's like the enol is not isolated, are you talking about this like equilibrium thing where it's mostly gonna be these carbonyls, but there are some enol?
Yeah, maybe like 1% enol, 5% enol. But if you run this reaction in a lab and you take your product over to the IR to analyze it, or you put it into the NMR, you're not going to find evidence of the enol. It's not going to look like you ran your reaction and went home with an enol. So when you predict a product, you predict the carbonyl. That's the product that's formed. This example problem has one precursor in the middle that's not given to you. Going to the left, it gives you a certain product. Going to the right with different reagents, it gives you a different product.
Make sure you have your 2. You got your 1 and your 2.
You're going to work backwards from the left, but you're going to work forward to the right. Does that make sense? Predict the starting material, that gives you the product on the left. And it can also react with different reagents too. if you need to, take these example problems and map your carbons to figure out how the carbons of the alkyne become the carbons of the carbonyl, and then try to apply that mapping to this problem. Yep. It's the 1 and the 2. Good. Oh, actually, too many carbons here. That's it. How are you going to make sure you don't mistake the number of carbons next time? There you go. There you go. All right, I'm going to give you a hint. It's really not a hint. It's more like a, please do that. Number them, map them, so that you can figure out what your intermediate can all have, what your product can all have.
That one's the weak one too.
I'm sorry?
That one doesn't need it too.
That's correct.
It's only the.
Notice that it's just one name, oxymercuration,
Okay.
but this is two names, oxymercuration followed by reduction. Okay, I do want to chime in. I'm sorry about this. BH3 is not always the best reagent when doing this reaction with alkynes. It is the reagent that I'm going to put on your exams and unit tests because it's just easier to recognize and useful. But there are often borane derivatives. I know that on active, there is an example of a borane derivative. You can almost spot that it's borane because it has a B in the abbreviation of the compound name. But there's so many different kinds and they're just not easy to abbreviate. Borane gets the job done in a messier way. So they usually use some other borane derivatives. In your intermediate here, you should be looking for this 3-carbon chain to have an alkyne on it. The only place the alkyne can be is between carbons 1 and 2 as we've mapped them. Now, given that carbon 1 becomes the carbonyl and carbon 2 takes 2 hydrogens, that's anti-addition of H2 and O. That's an aldehyde that forms. So my reagents here would be 1, BH3, followed by H2O2, H2O, and NaOH. Anti-Markovnikov hydration. If I take that terminal alkyne and I react it in Markovnikov conditions, I get a ketone instead of an aldehyde. Acetophenone on the right, 2-phenyl ethanol on the left. You'll never isolate this. So what you should predict is the carbonyl. But I do want you guys to recognize that there is an intermediate that forms, but it reacts with the acid, and this is the product you isolate.
So that's why it's reversible, but it wouldn't show up.
Yeah, that's right. Equilibrium favors forward direction.
How quickly does it convert to
Probably faster than you can blink. I mean, reactions happen very quickly. So, I mean, if you're saying like all of it, by the time you're done with the reaction, it'll all be converted.
It's not like you can sneak in reagents reactively on tests.
No, in fact, my OCHEM 2 class right now, their section is all about enols and their conjugate bases, enolates. They actually react mostly from that carbon of the alkene, not from the alcohol. So it's not possible to isolate it. They're very sneaky species. Okay, I do want to give just one last example, which is, what if I have this internal alkyne, especially if it is unsymmetric? What reagent can help me get there? And what is the missing product? So my oxymercuration reagents definitely work. Why? I get a ketone, and that's what oxymercuration is good at doing. It makes ketones. If I used hydroboration oxidation, would I get an aldehyde? There's no way that this alkyne can make an aldehyde. So if I did use hydroboration oxidation reagents, I still get the ketone. It's no longer Markovnikov or anti-Markovnikov. So the regiochemistry that we said before doesn't really apply here. Hydroboration oxidation only makes aldehydes, but that only occurs on this less substituted alkyne carbon. If they're equally substituted, there's no reaction, or no difference. So which one would you want to do? Well, it's either run 2 steps, which is just longer to do when you're working in the lab, or it's work with mercury. Pick your poison, literally. Now, to predict the other compound that forms, I'm going to look at the compound that was given. My alkyne was between carbons 2 and 3 when I map it this way. Why did the ketone only form on carbon 3? Was it more substituted than carbon 2? So I also get a ketone at carbon 2, or position 2. Good? Okay. Moving right along. Reductive hydrogenation. Bit of a redundant name because adding hydrogen to a carbon chain is always going to reduce its oxidation state. In our generic example here, we'll use hydrogen with our same palladium on carbon catalyst. Alkyne to alkane. Very similar to last time where we saw an alkene to alkane. No chiral carbons can form because you'll be adding 2 equivalences of H2 to both carbons. Sorry, 2 equivalences of H to both carbons. H2 is always in excess. We don't have to say it. You'll never see it explicitly stated. You're welcome to say excess next to H2, but there's no way to run this reaction not in an excess of H2. Regiochemistry? Not really. There's nothing to consider. You just add hydrogen to both carbons. Stereochemistry? No. No chiral carbons formed. 7. Partial hydrogenation. A couple of ways that you could name this. Lindlar's catalyst reaction, or the cis-alkene reduction. I know you don't know what those mean yet. You're going to see it in the example. In our generic example, the alkyne reacts with H2, but this time we don't react it with palladium on carbon. We're going to write over the reaction arrow Lindlar's catalyst. Lindlar's cap. And Lindlar's catalyst is the palladium on carbon catalyst, but also quinoline and barium carbonate. It's actually not a catalyst that helps a reaction proceed. This is a poison catalyst. Alkenes will no longer react. Only alkynes will react. So this reaction gives us a cis-alkene. Notice that the two hydrogens that have added to the same face. So in terms of regiochemistry, there's nothing to see. And in terms of stereochemistry, this is syn addition.
That makes it zero.
That's Z, yep. That should ring a bell. Hydrogenation was syn addition with alkenes. And now it's syn addition again. In fact, this reaction is also syn addition. It's just syn addition times 2, so you can't tell that it's syn addition. Because you end up with these achiral carbons. But when you get a stereocenter alkene, you know that it is syn addition. This partial hydrogenation is the first step of this full hydrogenation. Without Lindlar's poison catalyst, this alkene forms. But then, as we know, this alkene continues to react. We know that alkenes react through hydrogenation, and it just gets reduced down to an alkane. Lindlar's catalyst is a poison that allows us to capture that cis-alkene intermediate and utilize it. Because that can be useful. What if I don't want a cis-alkene? This is the metal ammonia reduction, or metal ammonia hydrogenation. Our generic example here reacts the alkyne with metallic metal and liquid ammonia to give us a trans-alkene. I want to make this very clear. That is not sodium ion. That's sodium metal. How can you be so confident on that? No charge, and it's not written as a compound. It's not bonded to anything. It's not sodium amide. Actually, sodium amide is a byproduct of this reaction. 2 hydrogens get added across the alkyne, 1 to each carbon, which means 2 equivalences of ammonia have to get rid of their hydrogen to give us sodium amide. Sodium has how many electrons to give away? This is a 2-electron reduction of the alkyne. So I need 2 equivalences of sodium to each give away their 1 electron. So in terms of regiochemistry, nothing to talk about. But in terms of stereochemistry, this is an anti-addition transalkene product. Okay, now I think it is super cool to see the mechanism for this, but it's not a mechanism I'm going to have you regurgitate, so I'm going to leave out the electron arrows. And if you want to add in those arrows, you're welcome to. And I'm also going to put this in quotation marks because it's not a true mechanism without arrows. The first thing that happens is that sodium donates electrons to the alkyne. That alkyne has full octets everywhere. So in order to give an electron to the alkyne, it needs to break a pi bond. Creates a radical on one carbon and a lone pair on the other. And there's actually 2 configurations that this can show up as. It can show up as a cis configuration where the lone pair and the radical are adjacent to each other, or it can show up as a trans configuration where the lone pair and the radical are anti. Do you know what type of electron repulsion is the strongest? Lone pair to lone pair to bonding pair, or bonding pair to bonding pair? Lone pair is the strongest type of electron repulsion. Technically, we don't have 2 lone pairs here, but we do have a lone pair and a lone electron, which means this is going to experience a lot of repulsion. And it's not going to be the energetically preferred configuration. So the trans configuration shows up. This step also gives me sodium ion. And it's this next step where this lone pair deprotonates ammonia, gives me the hydrogen, and kicks off an equivalence of NaNH2. Is the mechanism done? I don't have a transalkene yet. I still have a radical. So here is where the second equivalence of liquid ammonia and metallic sodium come into play. A second electron is donated to the radical, creates a lone pair, balanced by sodium ion. That lone pair deprotonates ammonia, leaves me with my second equivalence of NaNH2 and my alkene. Here's another fun application of acid-base chemistry. We use sodium amide to deprotonate alkynes because the alkyne is a better acid. And we use ammonia to protonate alkenes because ammonia is a better acid. Amines sit right in between the acidity of alkynes and the basicity of alkenes. So we can actually form ammonia by deprotonating an alkyne, and we can consume ammonia by protonating an alkene. The only difference is the hybridization of the carbon, but it makes a pretty meaningful impact. Okay, let's do some examples. Symmetric alkyne. 3 different reactions. In order to fill in those reagents, you got to figure out what change is happening. You've got to be able to recognize the stereochemistry and the functional. Okay. Full hydrogenation with our normal conditions, H2 with PDC. If I map my carbons like this, then I can keep track of my product, 1,2-diphenyl ethane. Transalkene, cisalkene. From the same alkyne starting material, I need ammonia with metal. You know what? There was something I wanted to say. You notice we don't call it sodium ammonia reduction. That's because we can also use lithium. So there may be places where you see lithium used in place of sodium. Does the same thing. Some of you might recognize that I put Na over NH3, but here I have Na comma NH3. Are those different? Just a totally different way of writing it. This is a list instead of a column. Here, I need hydrogen, but I also need to poison my reaction with Lindlar's catalyst. I'm not a big fan of just writing things up there that say Lindlar's catalyst, know what that means. But quinoline and barium carbonate don't really explain why it is a poison catalyst. So it's easier to just write Lindlar's than to put what it actually is. Otherwise, I generally enjoy you guys seeing what the actual chemistry is. But it doesn't add anything to your intuition. All right, any questions so far? Okay. We've done X2, HX, hydration, hydrogenation. We're not going to see epoxidation. We're not going to see diol addition because you guys recognized our alcohols never even stayed alcohols, they transformed into carbonyls. So no diol addition, but we are going to see oxidative cleavage. The last time we saw this, we actually saw two types: reductive oxidative cleavage and oxidative cleavage. Here we're only going to have one type. So in our generic reaction, we're going to use ozone with hydrogen peroxide, or we're going to use hot potassium permanganate. I have intentionally given us a terminal alkyne because an internal alkyne is going to create two of the same functional groups, two carboxylic acids. But a terminal alkyne is a bit unique. One of them, the more substituted carbon, and let me map my carbons so you can see what I'm talking about. The more substituted carbon of the alkyne becomes a carboxylic acid. The other carbon also becomes a carboxylic acid, but when it's terminal, you don't isolate that carboxylic acid. You actually isolate carbon dioxide. It decomposes. We saw this in the alkene oxidative cleavage. That if you're not careful, if you've got a CH2 group on your alkene, it produces carbonic acid, which decomposes into carbon dioxide. Same thing here. So in other circumstances, when there's an internal alkyne, two carboxylic acids. That'll be the regiochemistry for this. That's it. But there's a lot of ways that we can combine these reactions together. I want to take 2-pentyne, and I want to make SS2,3-dibromopentane. Earlier, Jamie said, maybe there's a reaction that will help me add 1 hydrogen and 1 bromine to each carbon. But there isn't a reaction. We've seen them all. There is no reaction that adds 1 bromine and 1 halogen, which means the only way for me to get 1 bromine and 1 hydrogen to each carbon, I have to use more than 1 reaction. Does it look like these 2 bromines have been added anti? They look syn to each other, right? So I need to do a halogenation step, and I need to do a hydrogenation step. I'm going to add halogens to both carbons, and then I'm going to add hydrogens to both carbons. Which order should I do them in? Let's see. If I add H2 with Lindlar's catalyst, I'm going to get a cis alkene. And if I take this and I do halogenation across the alkene, it's going to give me this anti-addition product, which is not in its lowest energy conformation. And so all it has to do is go through that rotation, and it gives me my final product. Although I know this might seem like nitpicking, but I actually put the wrong stereochemistry for the product that I'm showing. If I had done metal ammonia reduction, I would have gotten a transalkene, and the anti-addition, sorry, that's probably invisible. The anti-addition onto that transalkene, it's going to look wrong. Not look wrong, sorry. The stereochemistry will be wrong. The bond line is in the correct conformation, but the stereochemistry of the bromines is incorrect. Which means if I had used metal ammonia reduction, I would have gotten the wrong alkene. But there is actually another way to get this same product. There's another route. First, let's react with Br2, just one equivalence. And get this trans dihalide alkene. And then hydrogenate the alkene. Hydrogenation is syn addition, so it takes those two halogens and it puts them onto the same face because it puts the hydrogens onto the same face. Two different routes. Both involve one step of halogenation and one step of hydrogenation in specific sequences. Multi-step synthesis is so common. This is a pretty specific example, but you guys could see how do you get from a geminal dihalide to a carbonyl compound? Well, you can run elimination to get an alkene or an alkyne, and then do oxidative cleavage on that alkyne to split it into the carbonyls. So, multi-step synthesis is coming. This is where we start adding all of these reactions in sequence to each other. I don't think that I have enough time to get through all of this. So where we're picking up on Monday is a very short section on alkyl halides. We're really probably going to cover it in like the first half hour. And what we're going to look at in that section is called radical halogenation. And we're going to look at anti-Markovnikov HX addition. Radical halogenation is actually a substitution reaction. These are new reactions that are basically just review of what we've seen, and they're going to set us up for more multi-step synthesis when we start learning more about elimination and substitution reactions. And then we're going to try and take all of this and blend it into our last type of reaction next week called the Diels-Alder cycloaddition reaction, where we'll be able to start making six-membered rings in our products by adding two different compounds together. Is it a lot? Yeah. Is it kind of repetitive? Yes. What's the best way to get familiar with all of these different reagents, the functional groups they form, how they react? Make a table. So I'm giving you guys tomorrow off so that you can go and spend the hour and a half you would be here in class crafting a table of reactions. Organize it by the functional group you start with, the functional group you end with. Look at how to prepare alkenes, prepare alkynes, add to alkenes, add to alkynes, alkylate alkynes. And next week, we're going to finish it all off with substitution and elimination and Diels-Alder. And these. All right, guys. Have a good weekend.
Is there a bunch of